Assalamu alaikum. Welcome to our latest explainer. Today, we're setting out on a really fascinating visual analysis to understand something profoundly important. We're going to look at exactly how we measure change in the real world using some of the most fundamental building blocks of mathematics. Seriously, these mathematical concepts dictate everything from the trajectory of a rocket launching into space to the hidden underlying forces that are shaping our global economy every single day.
Now don't worry, we're taking a step-by-step building block approach here. So here's our agenda. First, we'll cover the core concept of limits. Second, we'll explore the unbroken path, also known as continuity. Third, we'll see how this acts as the engine of calculus. And finally, we'll tie it all together with real-world economics.
All right, let's jump right into Section 1, the core concept of limits. Okay, let's dive into this. Imagine you're walking down the street toward a specific destination, like, say, your favorite local cafe. A mathematical limit isn't necessarily about actually opening the door and stepping inside that cafe. It's about the journey itself. It's about where your steps are consistently taking you as you get closer and closer. Formally speaking, a limit is the value a function, we'll just call it f of x, continuously gets closer to as x approaches a specific target point. So it is purely about the behavior of getting near a point. In fact, the function itself might not even exist at that exact target, but the limit still can, because again, the limit only cares about the approach.
So the crucial point here is that distinction between the journey and the actual destination. On one hand, tracking the limit of f of x as x approaches a focuses purely on the behavior, that journey toward the destination. On the other hand, you have the actual value of f of a, which is the exact literal destination itself. And in mathematics, these two things don't always have to match up. The limit is basically asking, what does it look like is going to happen based on the trend, completely regardless of what actually exists at that exact final coordinate.
Let's put this into practice with a super simple, intuitive example so you can see this behavior in action. If our function is f of x equals x squared, as our x value approaches 2, the limit approaches 4. It's totally predictable and smooth. As you slide closer to 2 on the graph's horizontal axis, the output just naturally slides closer to 4. And in this specific, highly predictable case, the actual value at the exact point of x equals 2 also happens to be 4.
Which brings us nicely to Section 2, the unbroken path, or what mathematicians call continuity.
So what happens when that journey and the destination match up perfectly, every single time, without any interruptions? Well, in simple terms, continuity is a state where a function has absolutely no breaks, no gaps, and no sudden jumps at a given point on a graph. Think of it like this. If you can draw the line of a graph with your pencil without ever having to lift that pencil off the paper, that function is continuous. There is absolutely no break in the mathematical path.
Now, for a function to officially be deemed continuous at a specific point a, it really has to pass 3 very strict rules. First, f of a must be mathematically defined, meaning the destination actually has to exist. Second, the limit of f of x as x approaches a must exist, so the journey toward it has to be completely clear from both the left and the right sides. And third, the limit of f of x must perfectly equal the actual value of f of a. The journey and the destination have to match up flawlessly.
But consider what happens when those rules get broken. Take a look at the function g of x equals x squared minus 1, all divided by x minus 1. If you track the limit as x approaches 1, the math actually simplifies, and the path aims right at the number 2. So the limit exists, and it's 2. But if the function is defined so that g of 1 actually equals 0, the path breaks. It's literally like walking across a perfectly sturdy bridge expecting to step onto the next wooden plank, but there's a gaping hole, and the actual plank is just sitting down in the river below. The limit exists, but because the function's value breaks from the path, we get what's called a removable discontinuity.
All right, let's pick up the pace and dive into Section 3, the engine of calculus.
Let's move on and see how this builds, because these seemingly simple ideas of approaching a point and ensuring an unbroken path act as the absolute bedrock for advanced calculus. First, we have limits, which we just covered. Once you understand how to approach infinitesimally small distances, you unlock step 2, derivatives. These allow us to calculate exact rates of change at a single instant. And from there, we reach step 3, integrals, which use the concept of limits to sum up infinitely small parts to find total areas. The big takeaway here, literally none of this higher-level math works without the foundational step of limits.
Just look at the fundamental formula for a derivative. f prime of a equals the limit as h approaches 0 of the function of a plus h minus the function of a, all divided by h.
Now, you totally don't need to memorize the algebra right now, but just notice that lim right there at the very front. Measuring a rate of change, the derivative itself, is entirely dependent on taking a limit. Without it, calculus simply cannot exist. It's absolutely crucial.
Let's bring this all home in Section 4, Real-World Economics.
So you might be asking, why does any of this abstract math actually matter in the real world? Well, it's because economists rely heavily on limits and continuity to model our modern economic systems. These tools are completely vital for calculating things like marginal cost, marginal utility, and for building continuous market models. By taking the limit as a change gets smaller and smaller, economists can precisely understand how infinitesimally small changes in one variable, like, say, tweaking a factory's production just a tiny bit, will ripple out and affect broader economic outcomes.
And this distinction is a real game changer for policymakers. Under continuous policies, a small intervention, like a tiny fraction of a % interest rate tweak, results in predictable, smooth changes because the underlying market model itself is continuous. But on the flip side, we have discontinuous policies. If there's a break or a gap in the market model, a tiny change could result in totally unpredictable jumps, sudden spikes, and just massive volatility. Continuity is what ensures our economic models remain stable and our policies have predictable outcomes.
Let's zoom in on one specific, super vital metric, marginal cost, or MC. This is mathematically defined as the derivative of the cost function with respect to quantity, or dC over dQ. If a factory's cost function is continuous, producing just one more tiny unit, that dQ, uses the exact mathematics of limits and derivatives we've been talking about to accurately calculate the marginal cost. The math of infinitesimally small limits is literally what gives businesses exact, actionable numbers on profitability and scale.
Okay, let's wrap this up and review our core takeaways from today's analysis. A limit is purely about approaching a specific value, the journey. Continuity is that strict mathematical requirement ensuring there are absolutely no breaks in a path. Calculus, as an entire field of mathematics, is built completely on the foundation of limits. And economics relies strictly on these limit-based derivatives for accurate marginal analysis. So you see, these aren't just dry textbook equations. They are the very real, fundamental tools we use to model, predict, and ultimately stabilize our incredibly complex, continuous world.
Which leaves us with something pretty profound to ponder. If we can mathematically predict the exact behavior of complex systems using infinitesimally small increments, what actually limits our ability to predict the broader future? Is it just a lack of continuous data? Or are there fundamental, unavoidable jumps in reality that we just can't calculate? I want you to really think about that as you go through your day. Thank you so much for joining me for this explainer. Allah Hafiz.